Good morning, you guys. Happy Monday. Yeah. Okay. I hope you are all doing well and had a restful weekend. So I want to let you know that I was able to look at the expectations you guys wrote from the expectation sheet we did last Monday. And I just so you know, I can't see your names. So if you told me something and you're like, well, I thought I told you on that expectation sheet, I don't know who wrote what. Okay. And I kind of did that to give you guys a feeling of like freedom to say whatever you wanted to say. So I cannot see names, just to let you know. One thing I did want to tell you from looking at things you guys wrote out of expectations for yourself was it's hard being in this digital kind of learning environment to create like study groups. So some of you might already know other people in the class, but maybe some of you don't know anyone in the class. So I hope eventually you guys will use each other as a resource, you know. So when I put you in breakout rooms, maybe you can say, hey, can I get your email so we can set up, you know, a study session or a study group. Or if anyone does set up, you know, like a study group and you're willing to have other people join you, you can let me know and I can post it on the Canvas page, okay? Because I'm sure there are some people that would appreciate that. And just getting a, you know, so there you guys can, having each other as a resource is important, and that might be hard to facilitate now that we're all at home. So again, either try and get each other's emails, or if you're having a session and you're willing to open it up to the whole class. And from experience, I feel like not that many people would go, but I know there'll be a few people who would probably appreciate it. You never know with this class though. I feel like people in this class they work really hard. So that's awesome. Okay. So some expectations for me that you guys wrote about was post the recordings and posting slides. So that's my plan. I have all the slides up there. I just have to, you know, make them visible to you guys. So if for some reason the slides are not visible, just kind of send me a reminder. I appreciate reminders. I told you guys I had that mishap with my laptop on the first day of class. So I recorded to that laptop. I'm having trouble accessing it. So I was able to post Wednesday's video, but I haven't been able to access Monday's video, which was our first day of class. Most information's in the syllabus, but I am still trying to access it. But that's the only reason I haven't posted Mondays. I do plan to post all the recordings from now on. So someone put an expectation to go over the workbook questions at the end of class. And sometimes, and I'll be honest with you, we'll run out of time and I won't have a chance to go over the questions at the end of class. And so what I'll do is I'll post a key to those workbook exercises. I'll put a key up. And again, remember we talked about you taking responsibility for your learning. So I'll put a key up and then you guys can look at the key. And then if there's something that's not clear or you have questions about, you can come to office hours. And I don't even mind if you ask at the beginning of the next class, like, hey, Dr. Laris, we did this group assignment on our last class. I looked at the key. I was still unclear on this point, you know, and I'm sure other people in the class would appreciate that. So that's kind of what I've done in the past is like, if we don't have time to go over it all together, I usually post a key anyways, but I might be under the expectation that I posted the key, you can check it out and let me know where you're still unclear. Okay. Someone else wrote expectation of responding within 72 hours to an email. And so I do try to respond to email pretty quickly. I can sometimes not respond to email. So you guys can please just send me a reminder. But I noticed with the digital learning, I don't know if last semester I was just getting used to it. Sometimes I wouldn't respond to people's emails, but it was usually because like they were asking me something like, can you send me a study guide? And it's like, I posted it on our Canvas page. I emailed you guys that I posted on the Canvas page. And I mentioned it in our video that I posted on the Canvas page. I get like 50 emails a day. So someone sends me an email saying, can you send me a study guide? I'm like, next, on to the next one. And I don't know if that's rude. Maybe I need to be more, I don't know. Maybe I need to work on that. I'll try. But sometimes if I posted it and I sent an email about it and I've said it in class, I'm usually not going to respond to it. Like I said, I need to work on that. You too, you guys can take responsibility for your learning too. So check in all those places. But if you feel like you're asking me a question, I'm not responding, send me another email. Because like I said, I get like 50 emails. And so sometimes I overlook it. So don't necessarily think that I'm ignoring you on purpose. Okay. So I do try to respond, but sometimes I'm just like, I already posted that. Okay. And then there was another expectation about teaching different material. And so, like I said, you guys are going to take responsibility for your learning, and there's just no way that I can teach and meet everyone's needs in the class. Okay. And so that's where I really want you guys to advocate for yourself, and figure out what works for you. Okay. And so, again, I know some people do really well by coming to office hours. That really helps them. Or they do really good by getting a tutor through the Lark Center. Okay. Or they do really good by, having their own study group. Okay. And so you guys need to figure out, again, what works best for you. Okay. Questions on expectations? And I know sometimes it takes us a minute to find the unmute button. So sometimes when I ask a question, I feel like I need to give you guys a longer time to respond. Okay. Okay. You guys can feel free to email me or put something in the chat or unmute if something comes up for you. Another thing I wanted to address was our group assignment questions from last week. So I went ahead and gave people, if you guys turned it in, you earned the points for both the writing assignment and the group assignment. So just real quick, there was that question, do organisms disobey the second law of thermodynamics? And several of you, well, so there was mixed answers. And I want to just clarify that no, organisms do not disobey the second law of thermodynamics. It may appear that way because we're well organized, but there's an exchange always between us and our surroundings. And for instance, we take plants in, right? If we eat a plant, it's a highly organized, molecules, right? We chomp it up. It's solid, right? We chomp it up, we break it up, and we release it as gaseous carbon dioxide, okay? So remember when you were learning about entropy, going from solid to liquid is an increase in entropy. Going from liquid to gas is even furthermore increase because gases, right, can spread out. So just think like we take in solids and release it as a gas. So we are not, there's an exchange going on. So even though we look highly organized, we are also creating disorder as well. Okay. All right. All right, you guys, exciting stuff. So today we will finish kind of our review of stuff you've seen before. And then on Wednesday, we should get started on our glycolysis. Okay. And just a little heads up. I'll share my screen. Okay. If you go to our Canvas page, under week 2, this is a group assignment for today. So you guys might want to, have that open somewhere or be writing down any questions you might have or answers your group comes up with, because that will be due at the end of today at midnight. We won't go over these chapter 14 slides until again Wednesday. We won't get into those till Wednesday, but I put them up so they're there for you guys to look over. And there is going to be this class prep assignment. So let's do before class on Wednesday. Okay. So that should be pretty straightforward, but yeah, you'll have this prep assignment for Wednesday. Okay. Questions? Okay. So let me stop share here. All right, I'm gonna try something I feel like is risky here. Okay, yay. I'm gonna share slides, I think, from my iPad. Ooh. Okay, so give me a second here. Oh God, don't do that to me. Okay, well, so someone said that we're continuing on with section 5.1. Yes. So we're going to continue with 5.1, but we're not going through that whole section. We're doing all of 5.1, but then it starts going into oxidative phosphorylation, which we won't do until later. Okay. Again, on Wednesday, we're going to start on glycolysis, and that's in section 6 of that online text. I will look up the page numbers and email those out because I know navigating that wasn't straightforward. Okay. All right. So I think I'm gonna have to share from this screen. All right. All right. Okay. So and you guys, I'm sorry, my edited slides, I have a lot of other stuff too, but those are good questions for you guys to think about. All right, so today we're going to start looking at some of the organic chemistry. And the reason we go over this stuff is because we'll use these terms, and I want to make sure we're all on the same page. And remember, also, if you can remember some of your organic chemistry, you can start to instead of, like I said, you might start memorizing glycolysis or citric acid cycle or something like that. But if you can use your chemistry knowledge, it starts to make kind of chemically logical sense, like what the next step needs to be in order for certain things to happen. Okay. So that's why we look back at this organic chemistry, because you can start to again, you don't have to necessarily memorize. You're like, well, I know this bond has to break, therefore this is going to have to happen, Okay. So let's look at some of this vocab. All right. Okay, so if we in metabolism, we're gonna make a lot of carbon-carbon bonds or carbon-hydrogen bonds, and we're gonna break a lot of bonds because we're talking about breaking down large molecules and building up large molecules. So in homolytic cleavage, it just means if you break a bond, right? We think of bonds as having 2 electrons. Homolytic cleavage means each, side of the breakage gets 1 electron. Okay. So in this case of this carbon-hydrogen bond, if it breaks, we end up with a carbon radical, right? And remember, a hydrogen with 1 electron is a hydrogen atom, okay? Which is different than a proton, which is different than a hydride, okay? If we had homolytic cleavage between a carbon-carbon bond, then we just end up with 2 carbon radicals, okay? In heterolytic cleavage, we don't have this kind of same separation of electrons, right? One of the atoms, in this case the carbon, got the 2 electrons in the bond, and it formed a carbanion. So remember that term, right? Anion, meaning a negatively charged atom. Okay, so this is our carbanion. It has these 2 electrons here, that lone pair with a negative charge. And the hydrogen involved didn't get any electrons. It's left with a positive charge. So again, hydrogen with no electrons is what we refer to as a proton. Okay, lots of protons in biochem. Another heterolytic cleavage, again between a carbon and hydrogen bond, but this time if the 2 electrons end up on the hydrogen atom, you get a carbocation. Okay, you remember cation, positively charged ion. Okay, and a hydride. So hydrogen with 2 electrons and a negative charge is our hydride. Okay. And then if we had heterolytic cleavage between a carbon-carbon bond, we can end up with a carbanion and a carbocation. Okay, so that should be some review for you guys. Okay, so here's some examples of some bond formation. Okay, and so I'm not necessarily asking you guys to remember this as like an aldol condensation, but you remember that things that are nucleophilic like to attack the carbon of a carbonyl. We will see a lot of that in biochem. Okay, and so that's the formation of a carbon-carbon bond right there. Okay, we have a formation of a new carbon-carbon bond there. Notice our carbonyl got changed into an alcohol. Okay, so we went a reduction there. Okay, so that's an example of a reduction. This is a Claisian ester condensation. Again, I'm not so much concerned that you remember that name, but what I want you to realize is this is in pink here, right? This is a thioester. We'll have lots of thioesters in biochem. Okay, acetyl-CoA, you hear a lot about that. Okay, and so again, we have a nucleophile attacking the carbon of a carbonyl. This thiol group is a great leaving group. Okay, so a lot of times they'll be the leaving group in our reactions that we're seeing. So we have release of that group. We also have, again, formation of that carbon-carbon bond there.
Dr. Lauren?
Yes.
So I think I've been having difficulty like trying to discern reduction versus oxidation, but not because I'm confused on the definition of terms, but kind of because where you have a reduction, you also technically have an oxidation. And so like, how do you define like the aldol condensation as a reduction? Because I understand that our carbonyl is like getting reduced, but isn't the carbanion technically getting oxidized? So I think I'm just kind of confused there.
So the reason I call this in the aldol condensation, I called it a reduction. For one, there's a couple of reasons. This carbon had 2 bonds to oxygen, and now in the product it only has 1 bond to oxygen. So to me, whenever you end up with less bonds to oxygen, that's indicative of a reduction. You also have the addition of hydrogen. So it doesn't happen every time, but when there's more hydrogen in a molecule, then it's a more reduced molecule. So like if you think of like a long fatty acid that's saturated, that's like our greatest source of fuel, right? Is fats. And they just have all these carbon hydrogen bonds. And they're full of electrons, right? So it's a great place to siphon off electrons to power our bodies. Okay, and so and as we burn through our fats, those carbons, instead of having carbon hydrogen bonds, as they get oxidized, then they will form, right? Eventually they form carbon dioxide, carbon with
Did she get kicked out?
Yeah, I think so. I think she's, yeah.
That's fun. All right, Karishma, start teaching.
Go, Karishma, go.
Whoa, whoa, whoa. Chill out, Jacob.
Okay. Hello. Sorry, guys.
We can
Looks
hear
like I
you.
got kicked out for a little bit.
Yeah.
Okay. So I was talking about recognizing a reduction from oxidation. Where did I leave off there?
You were talking about
Phasing
CO2.
condensation and like algal condensation and stuff.
Okay. So again, I like what I was saying is that when I think of like fats, I think of saturated hydrocarbons, and they have that's a great source of electrons. That's a highly reduced molecule. And when we go through and metabolize them, we take them to carbon dioxide, right? Which is carbon with 4 bonds to oxygen. And so again, the more hydrogen there is, I think of that as a reduction. And we'll see lots of examples. I'll give you guys some other ways to recognize, like the names of the enzymes will help you recognize redox reactions. And again, looking at the carbon oxygen bonds as well. Okay. All right, so here, the last one on here, so these first two, the condensation reactions were formations of carbon-carbon bonds. This last one is a breakage of a carbon-carbon bond, okay? So we'll often see things form to have a decarboxylation.
All right, Christian, you're up.
All right, here we go. So as you guys can see here, I don't know what I'm talking about. So the book.
Okay.
No, oh no. Did she get kicked out again?
It looks like it. What?
Elizabeth, your cat is so darn cute. Oh,
This?
yes, yes. I need to pin your video. Okay. Oh my goodness.
Okay, sorry guys, I don't know what's happening. Me and Dr. Sher are both teaching classes right now. We're both getting kicked out. We're gonna have to get hardwired in. Okay. Let's try this again. All right. Okay. So you guys, there's these, okay. All right. You can hear me, right? Okay, great. Okay. So, there's this very interesting thing that happens. And so there's isomerizations that happen, and they don't just happen for no reason. Okay. So this is a step we'll see in glycolysis where we go from, we took glucose, we phosphorylated it, and we have glucose 6-phosphate. And there is a carbonyl at carbon 1. Then we go through this isomerization and we end up with fructose 6-phosphate. And then there's a carbonyl at carbon 2. Okay. So down here in B is kind of the mechanism of how it goes through that isomerization. Okay. So we have a base removing a proton, then the electrons in that bond, come down and form a double bond here, kicking these, the double bond of the carbonyl off to grab another proton. Okay, so we end up with a double bond and this OH group on carbon 1. Another base, a lot of times you guys will see these mechanisms. And I remember when I took biochem, I was like, where are these bases coming from? Okay, remember that a lot of these reactions, they're happening at the active site of the enzyme. So in this case, the enzyme's phosphohexosisomerase. And the whole point of the enzyme is it provides these bases and acids. So it abstracts a proton and it puts on a proton. So these are from the amino side chains making up the active site of that protein, of that enzyme, okay? So again, we have another side chain acting as a base, abstracting a proton here. Those electrons can go down and form a carbonyl that's now present at carbon 2, okay? So, sorry, I see something in the chat. Let's see. Okay, okay, so let's think about why this would happen, okay? I'm not gonna put you guys in groups right now to discuss this, but I just want you guys to think about this. What happens if in the next step, right? Because eventually, remember, you don't know this yet, but I'll tell you, maybe you do know, in glycolysis, you start off with glucose, which has 6 carbons, and you end up with pyruvate, 2 pyruvates, which is 3 carbons. And so you split the molecule in half here, okay? So guys, I want you to think about, if I'm gonna break this bond between carbon 3 and carbon 4, why, what's the difference of breaking the bond with the carbonyl at carbon 2 versus a carbonyl at carbon 1, okay? So take a minute to think, why, what chemistry is happening? What's the logic here? Why did our body go through this isomerization to move a carbonyl from carbon 1 to carbon 2, and then it's gonna break that carbon-carbon bond between 3 and 4? Think about that for a minute. All right. So if you guys think about that slide we saw on heterolytic cleavage, okay, and you think about what happens when that carbon bond gets broken, okay, you could end up with a carbanion here, okay? Now, if you have a carbonyl next to it, then that gives you a way to spread out like the electrons, okay? And it will stabilize the carbanion, okay? Whereas if that carbonyl was on carbon 1, it's not available to help stabilize the breakage of that bond, okay? So I just pointing this out because we'll see this happen over and over where carbonyl groups are getting moved and they're like 1 carbon away from where a bond's gonna get broken, okay? So again, instead of having to memorize, maybe that's where you start, but as you start to think about the chemistry, you're like, oh, okay, this should be the next step. Questions on that?
So would the carbonyl stabilize the carbanion or the carbocation?
A carbanion.
The
So you
carbanion.
could, yeah, like it could have the negative charge going, forming, in between carbon 2 and 3, and then the electrons in the carbonyl can come onto the oxygen since the oxygen's so electronegative.
Dr. Lars, I have a question.
Yes.
So if that 3 carbon gets the anion charge, then wouldn't the 4th carbon get the cation charge, and what would stabilize that? The oxygen?
So it's going to be different for each kind of mechanism where we see this, but there could be like a amino acid side chain in the active site of the enzyme that provides a stabilizing charge there. And we'll probably see other steps happen before the cleavage of that carbon-carbon bond.
Okay, thank you.
Okay. All right. Okay. So, something we'll see a lot is the hydrolysis of ATP. Okay, it's highly favorable reaction. Okay, so hydrolysis, hydro meaning water, lysis meaning break. Okay, so we're using water to break up ATP. So here's like a short version of the structure of ATP. You have your adenine base attached to your ribose ring, and then there's 3 phosphate groups. Okay, so this is our ATP molecule. Notice it has these 4 negative charges out here on this triphosphate group out here. Okay, so you could see water coming in here to attack. Okay, and remove one of the phosphate groups. Okay, so when this happens, the reason why this is so favorable, one thing is that it relieves some of that charge repulsion. So those 4 negative charges get relief when you break off a phosphate group with water. Okay, there's some stabilization happening in the products, helping make the products more stable. Okay, again, if you think back to the energy diagram we drew last Wednesday, the products here are going to be more stable than the reactants. So part of the products is this inorganic phosphate group, which will be represented by this PI. And so it can be stabilized through resonance. Okay.
Professor Laura's.
Yes.
How does it do nucleophilic attack if there's the negative charges on the oxygens there?
That's a good, so again, this is the products are highly favorable. And then there's usually going to have to be enzymes involved. And we want to look at, we're going to look at the thermodynamics right now. Okay, so keep that question in mind, because I do want you guys to think about something on the next slide that helps drive this reaction. Okay, and so whenever you guys are thinking about reactions, again, there's going to be some reactions that we're going to see. We're going to be like, wait a minute, that seems like it can't happen, right? So we have to be aware of, like, again, the thermodynamics involved, and kind of what the body is doing to help drive an unfavorable reaction. So this is actually really favorable because the products are so much more stable. Okay. But the body will do the reverse too. We'll make ATP, which is not a favorable reaction, but the body still does it. Okay. And again, this is one of the things we're going to look at throughout the semester. Okay.
What's the more favorable resonance stabilization of products? Oh, that's where it's showing with the PI group, the organic.
Yes.
Oh, okay.
Yes, the phosphate group, has resonance, so more stable. Okay. And then also it's showing you that this ADP, so with the 1 phosphate group removed, it can undergo ionization. So again, just the addition of a proton or removal of a proton, and that also helps stabilize the product here. Okay. So in that gray box, we have the overall reaction here. So here our reactants are ATP, okay, and our products are ADP, and then this inorganic phosphate group, okay. So if we keep in mind our discussions of thermodynamics, okay, from last Wednesday, why do you think cells, this is true, cells like to keep the concentration of ATP much higher than their equilibrium concentration? Okay, so like if we just allow this reaction to occur in a test tube, okay, not in an organism, it would reach equilibrium, and there's a certain concentration of ATP at equilibrium. But in our body, in a living organism, that concentration of ATP is held much higher than its equilibrium concentration. Why is that? Okay, I'm kind of afraid to put you guys in groups because of my internet's acting so bad. But I'm
Wait,
gonna do
Dr.
it.
Laura.
Yeah.
So this question is just like, if we look at the gray box on the previous slide, our body keeps it much higher to the reactant side. That's what we're saying.
Yes.
Okay.
Yes. Okay. So I'm gonna give you guys a like 2 minutes to go into breakout rooms. Let me see. Oh. Okay, maybe we are not gonna go into breakout rooms.
Does
Okay.
it have to do with like spending energy to make ATP? Doesn't it like you'd like use energy to make the energy kind of thing? And maybe
That
you
is
just need more.
true.
You need more of like a reserve of it.
We will have to definitely spend some energy to make ATP. But I was going back to the idea of the thermodynamics that we looked at last week. Okay.
Is it because ATP isn't very stable and it's used really quickly? So it's
ATP is less stable, yeah, than ADP, but we still keep the concentration pretty high.
Is it because it just makes it like, as we do use ATP, it makes it that much more favorable because we're shifting closer towards equilibrium and maybe increasing like the amount of delta G?
Ooh, yeah. See, now we're getting warmer. Okay. I'm gonna give you guys 2 minutes in your breakout rooms to discuss this. Okay. Sorry, I just got it to work on my laptop. So you can go out in breakout rooms and then we'll come back and talk about it.